One phenomenon that I should have looked at soon after covering Snell's law is total internal reflection, which, believe it or not, is responsible for your ability to stream Netflix and various other streaming services. Because even if you don't have, for instance, Verizon Files, well, it's not Verizon anymore. I think it's Frontier. Even if you don't have a fiber optic connection in your home, I'm fairly certain that at some point between the server and your home, the internet, the signals are being transmitted via fiber optics, and fiber optics rely on the phenomenon of total internal reflection. Let's start with just regular old light passing from water into air, hence the direction of the arrow here. We know that as the wave moves into a medium where it travels faster, it will bend away from the normal. If you want to know exactly how much it will bend, you use Snell's law. Here's Snell's law solved for theta 2 in terms of these two indices of refraction and theta 1. If my incident angle were greater, if the incoming ray came in at a greater angle to the normal, you would expect, since theta 1 goes up, this entire argument would go up, and that means that theta 2 would also come out bigger. My refracted ray would look something like this. I can continue this line of reasoning. As I make theta 1 larger, theta 2 will also be larger. And you start to recognize that eventually we're going to get to a theta 1 so large, or large enough, that the refracted ray will almost make an angle of 90 degrees with the normal. So this angle right here is approaching 90 degrees. It's not quite 90 degrees. Now, does theta 1 need to be 90 in order for theta 2 to be 90? No, because suppose theta 1 was 90 degrees. The sine of 90 is 1, and N1, water, has a higher index of refraction than N2. So this is a number greater than 1. Even if sine of theta 1 were equal to 1, because this is greater than 1, the entire argument would be greater than 1. And you can't take the arcsine of a number greater than 1. There is no real angle that has a sine greater than 1. So before we even get to 90 degrees, there's going to be some so-called critical angle, theta critical, at which the refracted ray really is 90 degrees. And then you ask yourself, is that really even refraction then? It's not like it's bent into the medium on the other side. It's almost like straddling the boundary between the two. In fact, if you were to go any further, that refracted ray would have to be on the other side. And that doesn't seem to make any sense, because what if theta 1 was this ray and then theta refracted came out like this? Do you see that the incident ray and the refracted ray are not making the same angle with the normal? In other words, that would be a violation of the law of reflection. So it seems that Snell's law is only valid if theta 2 comes out between 0 and 90. Beyond that, we can't even use Snell's law. You would have to just talk about the law of reflection. So don't forget the bigger picture here. When this incoming wave strikes the surface, the energy gets distributed in a couple different ways. Some of it will bounce off the surface. Some of it will reflect back into medium 1. Some of it will refract into medium 2. And the percentages, how much of the power is reflected back into medium 1 and how much of it is transmitted into medium 2, those things can be calculated using Maxwell's equations. In fact, I think those are synthesized into another set of equations called the Fresnel equations, and you can look at the percent transmission versus reflection in terms of theta 1. Of course, it's going to depend on theta 1. It will depend on the two indices of refraction. It will also depend on the polarization state of your electric field. Remember, if the wave's coming in like this, you can imagine the E field doing this in and out of the page, or this other perpendicular direction. So all of those factors will determine the way the energy is apportioned. We're not going to worry about that. We're just interested in the particular angle, theta 1, at which theta 2 comes out to be 90 degrees. That's the so-called critical angle. For any angle theta 1 greater than the critical angle, any ray coming in like this at an angle even bigger than theta critical, there would be no transmission at all. And that ray would simply bounce back into medium 1 according to the law of reflection. And that's called total internal reflection. Total meaning 100% of the incident power is reflected. It's not like 60-40, 60% reflection, 40% transmission. All of the energy, all of the incident energy, 100% would be reflected back into medium 1. And it's not hard to calculate theta critical. At theta 1 equal to theta critical, whatever, theta 2 would have to be equal to 90 degrees. That's the crossover point. For any angle theta 1 greater than theta critical, theta 2 would come out bigger than 90, and we know that doesn't work with Snell's law. So in other words, N1 sine theta 1 being theta critical would have to equal N2 sine of 90. Of course, the sine of 90 degrees is just 1. Solve for theta critical and you would get that it's the theta critical is the arc sine of N2 over N1. If I was on Jeopardy and I had to rapid fire answer this question, what is the formula for the critical angle for refraction of a light ray across a boundary between two media, I wouldn't be able to just regurgitate that formula. I don't necessarily have it memorized. It's not really difficult to memorize, but it's much more important that you just know how to use Snell's law and get the critical angle. It's the angle at which theta 2 comes out to be 90. And it's interesting to apply this to that most practical of examples that I just mentioned. Let me go over to PowerPoint here. We'll look at an image from your book. They talk about fiber optics. Let me see if I can maximize this. Okay. These fibers are extraordinarily small. They're smaller even than I realized. Just a few micrometers in diameter. That's maybe 1/10 the diameter of your hair. So that's kind of remarkable that they can manufacture such skinny filaments of glass. But this is one type of glass in the center, and it's got to be somewhat flexible. Maybe glass just is flexible if it actually is that thin. And then there's another type of glass surrounding this inner core that's called the cladding, and I assume it's also rather flexible. And then you've got this plastic cover on the outside. And your book explains if you were to do away with this, you would get tiny little nicks and scratches in here. And when you zoom up close on a scratch, that totally messes up the smooth surface, and you would lose this effect of total internal reflection. So focus your attention on the top here. You see how theta 1 here, well, it looks rather large, but the idea is, yeah, that's the whole point. Theta 1 is large because it's got to be greater than the critical angle. Remember, if theta 1 were small, if I'm trying to use the mouse here to gesture, if theta 1 were small, you would expect this ray to refract into the outside air. And then you've just lost your light energy. The idea is to get it from the source to the end. You know, this could actually be your modem if you've got fiber optics installed in your home for internet or whatever. And you like each of these contact points with the surface of the fiber optic cable to experience total internal reflection. So theta 1 needs to be greater than the critical angle. Remember, if your angle is greater than theta critical, theta 1 is greater than theta critical, you've got total internal reflection. That doesn't mean that there's no reflection if theta 1 is less than. Remember, at practically any angle, there's going to be some reflection and some transmission. But ideally, in a situation like this, you would like 100% reflection. And for that, your angle of incidence needs to be greater than theta critical. So let's use some typical values for the cladding and the core and see if we can figure out what that critical angle is. I can represent the core with this tube. And let's say the cladding is here. And then beyond that would be the plastic sheath. So plastic out here, plastic. This is cladding. And in here is the glass core. We'll label these indices N1 and N2. I don't know the index of refraction for the plastic. In fact, it may not even make sense to talk about that because the plastic is not necessarily transparent. But we don't care because we're hoping to have total internal reflection at the interface between N1 and N2. So let me just draw a representative ray coming in like this. Let's say, excuse me for a moment. I had to sneeze, and I'm not going to make a coronavirus this time because I've been following the news. This is starting to get real, so I guess it's not funny anymore. Here's a ray that came from further down the tube that way. Normal line. And I'll call this theta critical. If this angle of incidence really were theta critical, then our refracted ray would be coming out at 90 degrees to the normal. Okay, N1, I believe your book says, is 1.62. That's a typical value. And N2 would be the more familiar 1.50 for glass. And notice that this only works. You only get total internal reflection if N2 is less than N1. That's a fact I would try to just remember. Total internal reflection only happens if the index of refraction on the outgoing side is less than the index of refraction inside. So it would work from water to air, glass to air, perhaps even glass to water. Whatever it is, this one's got to be less than this one. I could just write down the formula, but let's just remind ourselves, N1 sine theta critical, that's got to equal to N2 sine of, the limiting case would be, 90 degrees. Sine of 90 is 1. So theta critical is the arc sine of N2 over N1. That's it. In this, arc sine. In this case, we've got 1.5 over 1.62. And do you see why? Here's another way of saying that N2 would have to be less than N1. If N2 is greater than N1, we would be taking the arc sine of a number greater than 1. That's no good. Let's ask the calculator what that angle is. 1.5 divided by 1.62, take the arc sine, 68 degrees, something like 68 degrees. Okay, so any incident ray coming in at an angle greater than 68 degrees would not transmit any power to the other side. 100% of that energy would be reflected. So I'll just imagine a ray coming in at an angle even greater than, I'll call this theta 1 greater than theta critical. We know that that ray is going to reflect entirely. And then I could use the law of reflection. I'm just eyeballing it here. And it's just going to bounce back into the tube. Same thing would happen here, and it would skip all the way down. And it's remarkable to read that these fiber optic signals, they don't just skip a couple feet down glass fiber. They can travel for hundreds of kilometers, and maybe one day that'll be even greater. Also keep in mind, your book talks about just two different media, a single layer of cladding. What's to prevent somebody from engineering or designing a cable with multiple layers of cladding? In fact, what if it was a continuously varying index of refraction? That might be interesting. I'm sure there are many applications of refraction where you've got multiple layers, each of which has a different index of refraction, maybe even continuously varying index of refraction. And I'm familiar with a few phenomena that are pretty interesting. I'll try to find time to make a lecture about that, like the sound channel in the atmosphere, the sound channel in the ocean involves some of this stuff. But you might also, those of you who are interested, check out negative index of refraction. I think maybe 5 to 10 years ago, that was a hot topic, probably still is, but you can do some pretty cool things with a negative index of refraction, like make a suit that makes you invisible. So I know people are working on this stuff. It's probably top secret at some of these defense companies. Google it.